We're in a race against the Nazis. And I know what it means if the Nazis have a bomb.
We have a 12-month head start.
18.
How could you possibly know that?
We've got one hope. All America's industrial might and scientific innovation connected here. A secret laboratory. Keep everyone there until it's done.
Let's go recruit some scientists.
In the film Oppenheimer, there's one hope. That one hope is to build a bomb. And there's one man who's qualified to help lead it. A person who is the foremost expert on quantum physics in the United States. J. Robert Oppenheimer. He has to assemble a team of heroes, but in this case, these heroes are scientists. There's a parallel between what the Manhattan Project was doing and what we're trying to do today. We're using scientists to solve for an existential threat. Today we're joined by returning guest, former Secretary of Energy, Dr. Ernie Moniz, who is himself an acclaimed nuclear physicist, the current head of the Nuclear Threat Initiative, as well as the head of the Energy Futures Initiative. Ernie is a perfect person to help us understand how the Manhattan Project relates to what we're trying to do today. I'm Jim McNeil, and this is Good Clean Energy. Ernie, it's great to see you. Welcome back to Good Clean Energy.
Good to be back with you, Jim.
You know, in thinking about the Oppenheimer film, we wanted to talk to somebody who could provide some perspective about, what it says and what it could have said. And I can't think of anybody more qualified than somebody who's run the Department of Energy and somebody who's currently at the top of the Nuclear Threat Initiative and the Energy Futures Initiative. So with that being said, what was your take on the film?
Well, I thought it was a very well done film, remembering that, of course, it has commercial objectives while telling a very serious story. And I thought it was a pretty remarkable narrative about Oppenheimer, the complexity of the person, the amazing job that someone who would never run any kind of a major organization could put together the Manhattan Project, marshaling the talents of world-leading scientists. Interesting dynamic between the security culture and the scientific culture. I think a lot of that really came out very well. The one part that I would have liked to have seen more of, although of course this may be my personal taste, would have been on the dynamics following the war in terms of Oppenheimer's push towards a very, very different deterrence policy than, of course, the one that we followed with huge arms buildups with the Soviet Union. That was exactly the issue at hand. It got obviously all tied up in the McCarthy era discussions, but that was one area where I would have liked to have seen a bit more depth on those discussions. Another amazing accomplishment of the Manhattan Project is also what took place away from Los Alamos in Oak Ridge to establish the enrichment of uranium, in Hanford, Washington, to establish the first critical piles to make plutonium. It was just an enormous, incredible effort, including the science of Los Alamos, but also the logistical expertise of setting up what were, in effect, two small cities to accomplish new technology.
I think it's really interesting to look at the film through the lens of today. I'm a big fan of major kind of governmental initiatives that do good things. I mean, if we look at the Apollo program, we got a man on the moon in 9 years. Manhattan Project took place in just 2 years, 11 months, I think.
I will note it was a similar time from the discovery of nuclear fission to the beginning of the Manhattan Project. Again, an amazingly short time to take some very fundamental science breakthroughs and convert them into a novel frontier technology development.
You mentioned, about the man Oppenheimer and the genius of Oppenheimer. This was a whole new generation of physicists. These were the quantum mechanics generation.
Right. Well, and Oppenheimer is given credit exactly for really, in many ways, introducing the quantum physics into the American physics establishment. And then, of course, especially given the pressure of what was viewed as a race against Nazi Germany, recruiting this global set of leading scientists, leading physicists to come together on this, a truly remarkable accomplishment.
The parallels between Oppenheimer's age and today's age are the Manhattan Project was in response to an existential threat of the rise of fascism. And today, we're responding to a threat of global warming and climate change. One that could be argued is even much greater than the rise of fascism in Europe. And the Manhattan Project wasn't just the birth of the atomic bomb, but it was the dawn of the fission age. And the fact that we have, 440 nuclear plants running in 32 countries producing 10% of the world's electricity? I mean, this is something that I think people don't really fully appreciate.
That's correct. And to bring it home to the United States, we have nearly 100 operating plants. And by the way, a new one for the first time in decades came on just recently in Georgia. The nuclear power system in the United States has provided roughly 20% of our electricity for decades. So fission has been an enormous boon to emissionless, carbon-free electricity, but fusion would take that yet up another step in terms of avoiding any issues that we have with fission. And unfortunately, we do have some that we still need to face.
So, Ernie, one of the things that comes up in the movie Oppenheimer is the fact that a fusion bomb, or what's now known as a thermonuclear weapon, would be 4 or 5 times more powerful than a fission bomb. And that's true. We understand that. What's the difference between fusion used in weapons and fusion used in energy? These are fundamentally different approaches. How are they different?
Well, first of all, as the Oppenheimer film stated, at that time, one was on the threshold of these thermonuclear explosions, and the fact that the yield would be an order of magnitude, let's say, larger than the atomic bombs was understood because the fusion process inherently releases a lot of energy. Fusion being, of course, the fusing of 2 light nuclei into a heavier nucleus. Right, so fusion is what keeps the sun going, but the sun has an amazing confinement mechanism. It's called an enormous gravitational field.
Yeah.
Well, on Earth, we have to use magnets and accelerators in combination to create the proper kind of, frankly, magnetic cage in a certain sense to confine an extremely hot plasma. If we do not succeed in that confinement, then the reaction is just self-terminating. So that public safety issue is not there at all. Now, in a weapon, however, one has essentially an instantaneous catastrophic release of that energy. In a fusion reactor, it is entirely different. One is having to construct through magnets, through accelerator beams, through various technologies, ways of trying to confine this highly heated gas or plasma of these light nuclei. The reason being that these light nuclei, any nuclei for that matter, but these light nuclei, they don't actually like to hit each other because they both have the same charge, same electric charge. And if you remember your high school physics, all of our listeners, like charges repel each other. That's why we need to get an enormously high temperature with a confined plasma so that the nuclei travel very fast and can overcome their repulsion and occasionally come together and merge and fuse. That's where the energy release then is enormous. But if you cannot confine, in this case, the gas, the plasma, then the reaction just doesn't happen and it just turns off. So it's a very, very different technology from a weapon, which is looking at exactly the opposite, a rapid, forced compression. And by the way, as was said in the film, the only way to get that compression in a bomb is to use an atomic bomb itself to produce the enormous pressures that you would need to bring it together for a brief instant so that you get a lot of fusion. Fusion device, again, just the opposite.
Right. You use nuclear fission as a trigger to create the heat and energy required to start fusion.
To compress the hydrogen gas, exactly.
In the bomb, and then it's all released as energy instantaneously. And the barrier you're talking about with atoms being repelled is the Coulomb barrier, right?
Correct. It's the Coulomb barrier.
It's the barrier that is the shield of the atom that has to be overcome.
Right.
And to make fusion happen. Yeah.
Because all atomic nuclei are, by our definition, positively charged, and they don't like to come together.
Right.
But in a fusion device, the whole idea is to sustain this gas confined, not touching any walls, at a very high temperature, the temperature being so high that the velocity of the nuclei has them overcoming that Coulomb repulsion,
right,
and fusing.
And what makes it so safe is that you have a vessel, which is a vacuum. You have a magnetic cage, which requires electromagnets. You have to feed it or provide fuel, which requires particle beams. And if any of these systems stop operating, or if the vessel gets breached, it just goes and it stops.
Correct.
Yeah.
Because you will not sustain that high temperature gas without having it confined. Again, it'll just dissipate.
Right, right. So fusion is inherently more powerful than fission. It's like 10 million times more energy dense than oil. And that's why it is ultimately the best power solution for the future of our planet.
And emission-free.
And emission-free, and in our case, with boron, radioactive waste-free.
Correct.
Yeah, okay.
Again, just to be technically correct, in terms of high-level, any kind of high-level long-term waste problem.
Right.
Yeah.
Right. Yeah, there is a modest amount of ash in a proton-boron reactor that may be radioactive based on secondary fusion reactions, right? Impurities in the system.
Well, but also the walls of the device will get a little bit radioactive, not much. But these are all problems that we deal with all the time. We should maybe emphasize that nuclear technology obviously is very important for energy, but it's not only for energy. For example, nuclear medicine is done in every hospital that we know of, and there are always low levels of radiation that are disposed of, but the nuclear fission reactor produces a whole new issue, which is the pieces of the fission process. The nuclei that are formed are very radioactive,
right,
and they stay radioactive for a long, long time.
A very long time, thousands of years.
Correct.
You know, the reason that the medical comment is really relevant is that the same rules that the NRC uses to govern nuclear medicine, radiotherapy, and the like will be similar to what we use to govern fusion, right?
Correct. The Nuclear Regulatory Commission has ruled that the regulatory arrangements for a fusion situation would be more like medicine or more like accelerator facilities than like a nuclear power plant of today, which is a whole different level.
Which is super important because the amount of time it takes for the NRC to approve a nuclear fission power plant tends to be very, very long, and we don't have the time to wait 10 years to get it.
Well, I'm going to defend them. They're doing better. But one of the issues is, a very serious issue, is the Nuclear Regulatory Commission, which, by the way, internationally is viewed as the gold standard of nuclear regulation. But the reality is their regulatory skills have been applied to only one technology, light water reactors,
right,
which are the kind that are out there today. But now today we are seeing a revival of interest in many other kinds of reactors, often called Generation 4 reactors.
Right.
And there the NRC has got a big learning curve still to mount.
Right.
But not for fusion.
So SMRs, small modular reactors, and Gen 4 reactors may have a longer path to certification and approval than a fusion reactor.
Yeah, the non-light water reactors, exactly.
You know, what happened in the Manhattan Project is we had this new generation of physicists who were the next stage after Einstein's relativity, you know, as we talked about quantum physics. What are you seeing today? You know, being at MIT and being in academia as you are you seeing a next generation of plasma physics coming up and to make this happen?
Yes. So in general, I would say nuclear science and technology generally is attracting a whole new generation of young scientists. Fusion in particular has this holy grail kind of label appropriately. And so we are seeing many, many different technologies being examined in the fusion space. And we are seeing many young people come into that. MIT is one of the places that has spun out a fusion technology. TAE itself is a spin-out from the University of California at Irvine. And I think these academic roots for many of these efforts shows the strong coupling, particularly to the young research community that is looking for making huge scientific breakthroughs, but is also looking increasingly to, frankly, addressing the biggest problems facing societies in the world. Global warming is certainly in the forefront of that, and fusion would be an amazing solution to many of our biggest challenges.
So going back to one of the points earlier, which is the Manhattan Project was in response to war, and one could argue that the Apollo mission was in response to the threat of war, right? I mean, it was the Cold War that really pushed the Apollo mission, the Sputnik satellite flying around at the end of the 50s. Is the problem right now that world governments don't really recognize, or maybe even the U.S. government doesn't really recognize clearly the substantial threat of climate change? And that's why we're not seeing the amount of money and effort that went into the Manhattan Project or Apollo Project?
Well, as we know, there remains today in publics various questions about the pace and the scale, the scope of addressing global warming. Now, I believe that the public attitudes are shifting dramatically towards calling for action because, for one thing, extreme weather is now identified by the publics as getting worse and worse. And frankly, as a consequence, costing this generation, not just future generations, but already this generation is paying a very high price for not addressing global warming aggressively. So there's no doubt that we are talking about a major transition in the energy system. But the reality is we really need collectively, nationally and internationally, to address global warming aggressively. We are getting further and further behind the eight ball on that. And that's where a real serious push on emission-less technologies, specifically including fusion, is so critical. I believe it's really critical that we succeed in at least demonstrating that we can do fusion for power in this decade so that we'll be able to earn the fruits of that in the succeeding 2 decades as we go towards net zero carbon emissions, at least in the industrialized world, by mid-century. Frankly, the scientific calculations about the implications of, say, doubling carbon dioxide concentrations in the atmosphere were made in the 19th century. They didn't have supercomputers, but they weren't that far off. As human beings, we have the agency to address this issue by moving towards an economy that does not emit greenhouse gases. It'll take decades to get there globally, but the longer we wait, the more the challenge is. So moving out smartly now is what we need to do. Frankly, in the United States, I think the legislation of the last couple of years has been very encouraging, although we will need to move towards more uniform national policy, hopefully then in sync with international policy. But there's no reason to not really start now. Well, we've already started, but to really pick up the pace now in terms of the technology development and deployment to have emissions-free energy systems.
And to get there with a clean, carbon-free solution could change everything, for the better.
Correct. And also things like industrial heat requirements. Not all, but much of that can be met quite affordably with clean electricity. So it's just across the entire economy that this would have hugely beneficial effects and provide the kinds of capacity additions we need for that increasingly electrified economy.
And so, Ernie, I think you're in D.C. today, so you're there with the Energy Future Initiative. What is the mission of the EFI? What are you trying to accomplish there?
Well, the Energy Futures Initiative is really all about bringing technically grounded analytical work to the clean energy transition. So we've had a number of threads in our work and our research and policy recommendations. And I might say, of course, we also don't have our recommendations just sitting on a shelf. We go out there and try to actively promote them. But as examples, we've had a major thread in hydrogen. We think hydrogen, again, has lots and lots of cross-economic sectoral applications in the future. large-scale carbon management, not just addressing today's emissions, but also being able to address yesterday's emissions, taking carbon dioxide out of the atmosphere, out of the upper oceans. We've had a lot of work, which we are still working on right now, on accelerating technology innovation. That would include the kinds of public-private partnerships that we think would be important for fusion. We've had a very strong focus on energy jobs and communities because we feel not only is that very important objectively, but it's also important for making political tailwinds for the low-carbon transition, making sure we don't have stranded workers and stranded communities. So those are some of the examples of our areas of thrust. I should have added nuclear. Nuclear in general is something that, of course, we also have been advocating for and advancing strongly. So across the board, one more issue that I will note, which also will be important in the fusion realm as well, but across the board, is the financeability of clean energy projects. The reality is that if clean energy projects are not there to meet the, shall we say, standard criteria for investors, it'll be very difficult to get the enormous private capital flows that we need. Estimates have been made that globally we'll need about $2.5 trillion a year to mid-century to accomplish the clean energy transition.
Yeah.
That's a lot of capital in terms of cash flow. So we are looking at how to advance the policy and regulatory worlds to make those kinds of investments blue chip.
Yeah. Well, 2 points. Number one, the carbon we have in our atmosphere today, may have been produced in the 1920s because it sticks around for about 100 years. So that's a really good point. And the second thing is that the impact that clean fusion energy can have on the world is so misunderstood because we didn't know that it was possible to build an atomic bomb. We didn't know it was possible to put a man on the moon. We didn't know it was possible to have a two-way video communicator in our pocket until we built these things. And until it's engineered and it's working, it's kind of magic. And I think fusion is still misunderstood as being magic when most of us that are deeply immersed in it understand its science and its engineering. Mm-hmm. And I think once it happens, people are going to look at it differently.
Well, and fusion still, in the minds of many, raises the old joke about it's 40 years away and always will be. And one of my messages is the joke has now been overtaken by events. I think that we will, in this decade, be able to answer the threshold question about achieving the conditions that can sustain fusion in the laboratory, in the power plant, and start delivering those benefits to society.
Well, I appreciate that quote, but my preferred fusion quote is that fusion will be available when the world needs it most. And I happen to think that's today.
Well, yeah, I was just going to say, I think that's not next decade. It's actually today. But right now, I'll settle for next decade to have a growing commercial enterprise.
Yeah, I agree. Well, Ernie, thank you very much for coming back to Good Clean Energy. You were our inaugural guest, so it's really wonderful to have you back again. And I hope we can do it again.
Terrific. Thanks, Jim.
Thank you for listening to Good Clean Energy.